This is a work that we have recently done in collaboration with these people, Ahmed Adami, Pujia Mao, Wahid Talinu, and Hossein Yavartanu. And this is a work in progress. Today I'm going to tell you about 2D and 3D cases, but the higher dimensional case and more general cases is coming up soon. This is regarding the symmetries at causal boundaries. So the problem that we are considering is basically in formulating physics, in particular gravity, in spacetimes where we have a boundary. And this boundary is generically a codimension 1 surface in the spacetime, and it could be time-like, space-like, or null. And the main idea that we are going to formulate is that whenever we have a boundary at the space, somewhere in the spacetime, which basically cuts the spacetime in 2 parts or is residing at the end of your spacetime in the asymptotic region, as we saw in the previous talk. For example, in the ADS, we have this causal boundary of the ADS. Basically, whenever we have this such boundaries in the spacetime, we need to introduce boundary degrees of freedom. In particular, actually, I'll be focusing on the cases where the boundary is somewhere in the middle of the spacetime. I'm not going to consider the cases like asymptotic ADS boundary or asymptotic flat space boundary. In such cases, basically, the spacetime is cut into 2 pieces by the presence of the boundary. And I'm going to focus only on one side of, and formulate physics on one side of this boundary. Basically, I'm going to excise the spacetime from by the boundary that I'm putting, and the boundary degrees of freedom are actually needed if I want to formulate physics in a consistent way by focusing only on one side of the spacetime. Okay, so this is sort of the question that I'm going to study. For the case of gauge or diff invariant theories, in particular gravity in this case, we can label these boundary degrees of freedom by the surface charges associated with the so-called non-trivial diffeomorphisms. And basically what we'll find is that in the 2 and 3-dimensional gravity cases, with the generic causal boundary, we are going to find 3 and 4, respectively, non-trivial diffeomorphisms and the associated charges, which can label the boundary degrees of freedom, and see how we can proceed from there. So this is the outline of my talk. I start with basically giving you a sort of review, very basic review of Einstein GR and the equivalence principle and how it should be amended in presence of boundaries. And then I'll focus on the causal, which I mean time-like or null boundaries in 2 and 3-dimensional cases. And I construct the solution space in presence of the boundary and work out the symmetries and the charges and the algebra of the charges and the technicalities which are involved in this analysis. I'll briefly discuss them, and if there are further questions, we can go, if time permits, we can discuss it in further detail, the technicalities, and I'll try to summarize and give you an outlook where we are going. Okay. So as you all know, Einstein GR is a generally covariant or generally invariant theory, and physical observables in the Einstein GR are all defined to be diffeomorphism invariant quantities. In particular, the metric, which is the dynamical degree of freedom in Einstein GR, is defined up to diffeomorphisms, a general coordinate transformation of this form. which, as you all know, transform metric in this way. And whenever we fix an observer, we partially fix these diffeomorphisms such that, for example, that observer is moving on along the time direction. This part partially fixes the diffeomorphisms, but there are generically some residual diffeomorphisms. Let me also briefly discuss the structure of the equations of motion and the degrees of freedom in Einstein GR. In d-dimensional case, we have a metric which has d times d plus 1 over 2 components, out of which d times d minus 3 over 2 are propagating gravitons, and then d of them are non-propagating degrees of freedom. They are just fixed by diffeomorphisms. We have diffeomorphisms in d dimensions. In particular, for the 2 and 3-dimensional cases that I'm interested in, as you can see, there are no propagating gravitons. These are the degrees of freedom as we have in the metric, and then we have the same number of field equations, Einstein equations, out of which, if we just write out these equations for the metric, what we'll see is that there are d times d minus 3 over 2 second-order differential equations for metric components, and then there are d constraints. These are the Bianchi identities, which are first-order differential equations. So you can see there is a perfect matching, as we all know from standard GR texts. We want to solve these equations. These are highly nonlinear differential equations, and there is no way to basically solve them in full generality. However, for the cases where we have, for example, Einstein gravity in presence, in the absence of matter, vacuum Einstein equations in 4 dimensions, or when we have, for example, Maxwell theory as the matter, we know that this is a Cauchy problem. We can solve the field equations completely once we specify the values of the metric components and its first time derivative on the given Cauchy surface. These are the initial or boundary data that we need to specify the solutions. However, regardless of whether we can basically perform the solution procedure completely and explicitly, we know that in order to specify the solutions, we need 2D functions over codimension 1 boundary. This codimension 1 boundary could be the Cauchy slice, or it could be some time-like or null surface in the spacetime. So these are the number of functions which we need. So these are functions over this codimension 1 boundary. And as we'll see, actually, these the same number of functions can label boundary degrees of freedom. So that's the main idea that we are going to formulate. So in this case, I'm interested in a causal boundary. So let me just explain what I mean. Let's suppose that I've chosen one of my coordinates to be r, such that r equals r0 is just some arbitrary value, is given by this causal surface, which the transverse, the vector normal to this is either null or spacelike. So the time direction could be along this boundary. This time direction I've denoted by v, and in general d-dimensional case there are d minus 2 transverse coordinates that are not depicted here. And I'll denote this causal boundary by C of r. And I've chosen my r coordinates such that r bigger than r0 is falling on one side, and r less than r0 is falling on the other side. And then we can have null rays, which could be infalling or outgoing null rays, both. And I'm going to be interested in formulating physics only on one side of this causal boundary in R bigger or equal to R0. I'm going to excise this part of the space-time, and then I'll need to add some boundary degrees of freedom on this, which are residing on this boundary, which basically are the substitutes of, for the part of the space-time and the degrees of freedom in R less than R0, which I'm excised from the space-time. In particular, note that when I'm dealing with a generic causal boundary, I can have infalling null rays or outgoing null rays. In the case where the boundary is a null surface, I don't have outgoing null rays because these null rays would be just moving along this surface, which is null in that case. Okay, so this is the kind of problem that I'm interested in. Once again, I want to formulate physics on this region, and basically the boundary degrees of freedom are needed to be added to account for the dynamics and the degrees of freedom in the part of the space-time that I'm not going to take into account explicitly. Okay. Good. In this talk, I'm going to focus on 2- and 3-dimensional cases. In the 2-dimensional case, there is no other direction in the space-time, and this is the whole space-time, and I'm going to sit only on this side. In the 3-dimensional case, I'll have another direction which I'll be denoting by phi coordinate, and is not depicted here. And in neither case, there are no, I'm going to consider pure gravity. And as I mentioned, in 2- and 3-dimensional cases, there is no propagating gravity, and so there is no infalling or outgoing null rays in my theory. Okay, so that's the kind of theory that I'm going to consider. And one more thing is that I'm not going to keep the causal boundary fixed, and I'll allow for this boundary to have fluctuations transfers to it, its direction. Okay. Okay, so with this setup and review, I'll just focus on the examples that I'm going to study. Let's consider the generic 2D gravity theory. Here, besides the metric, I have this scalar phi, and this x is some sort of potential term. This is a generic form for 2D gravity. Its equations of motion are given here. And you may be familiar with a particular member of this theory class, the JT gravity, for which this x of phi is linear in phi. Or another general family of within this 2D gravity theories could be obtained from reduction of Einstein gravity, generic d-dimensional Einstein gravity over sphere with this reduction ansatz, and which leads to x of phi of this form. And in particular, you can see that for d equals 3, if we reduce 3-dimensional gravity to 2 dimensions, we'll get JT gravity. So JT gravity is basically 3-dimensional gravity reduced to 2 dimensions. Okay, so let's start with constructing the solution space. The most general form of metric, which is compatible with having a boundary at a given R, is written in this form, where V has this form. This is basically coming from the solutions of equations of motion that I just showed. From solving these equations, we find this form. Phi is linear in R with 3 unknown functions of V, omega, eta, and lambda. And the V function in metric is written in terms of these functions through this equation. So as you can see, this the most general solution in this class has three unknown functions of V. They are not determined by the equations of motion, and one parameter M. Okay, and I'm going to restrict myself to cases where V is larger than 0, and basically this is where my boundary is sitting. So I'll just cut this space-time at any arbitrary R. Okay, so that's where I put the boundary. Okay, so one may ask, what are the remaining diffeomorphisms? There are diffeomorphisms which keep me within the solutions space that within the class of solutions here that I just showed. And one can readily, it's a very simple computation to show that this diffeomorphisms of this form, which are given by three independent, unknown and independent functions of V, T, Z, and W, rotate us within the same class of metrics. Just for the case of, for the fixing the conventions, I'll be calling T as V super translation because it's generating a generic local translation along the V direction. Z is R super translation because it's generating translations along the R. And W, which comes with this RDR, is a super scaling. By super here, I mean, this is just the usual terminology of this field. I mean local in V. So these are arbitrary functions of V. So they are not rigid translations in V or R or the scaling. If I drop the V dependence, this will be just rigid translations plus scaling in R. And in particular, note that this Z, which basically generates translations in R, as I mentioned earlier, basically as if it moves this boundary a little bit. So these are that Z transformation generates fluctuations in the transfer direction to the boundary, and it does it in a local way. So I mean, for each and every V, I have a different fluctuation function because this Z is a function of V. Okay. So I mentioned that this class of diffeomorphisms rotate me within the solution family of solutions that I showed. In particular, this means that, for example, I need to transform eta, omega, and lambda in this way. So if I transform them, basically, I'll remain within the same family of solutions. And M is a parameter which is basically not changing by the diffeomorphism. So it's just a number. Okay, so hence these diffeomorphisms are giving me the symmetries of this solution because it rotates us within this class of solutions. It's symmetries in the same sense that Noether has told us. Okay. One can compute the algebra of the symmetry generators. This is simply a bracket of these two diffeomorphisms. And this is the Lie bracket of these diffeomorphisms, which basically generates this algebra. And the T part is basically, for those of you who are familiar with this terminology, these super translations form a Witt algebra. It's centerless Virasoro algebra. The R super translations, which are generated by Z, and the super scalings, W form, as you can see from this term, a Heisenberg algebra. Okay, but there is also a killing vector for this class of solutions, this K, which is written this way. And this is not among the symmetry generators because these functions that appear here have are depend. I mean, lambda, eta, and omega have appeared here, which are functions which defining my solution space. They are field dependent in a sense. So these are not among the these C's that I just showed because T, Z, and W are taken to be field independent. Okay, so here I gave you the symmetry generators. Now I want to basically see how I can label these different points in the solution space through some charges, a la Noether. So I basically told you that we have some symmetries, and then you may ask what are the conserved charges associated with the symmetries. So, but then the formulation of Noether that we learn in standard courses is not good enough to basically capture this some features of the problem, the gravity case that we are interested in. There is this covariant phase space formalism, which is an extension of the Noether. We can discuss the details if you are interested in after the talk, but just for the time being, just view it as a Noether procedure. So we have some symmetry generators, and through some procedure, we associate conserved charges to this. There are some technical details, which are basically the details of coming from this covariant phase space method, but I'll skip those details in the interest of time. And among the other things in this covariant phase space formalism, one can basically show that there on the solution space there is a symplectic form which is acting on this, and basically this solution space is actually a phase space. In particular, I've just written for you the symplectic form for the solution space, as you can see here. It involves the three functions that I had and the same parameter that we had. This Y term is basically technicality, but what it does is that it allows us to define charges for any arbitrary R. Remember, I put my boundary at any given R. I didn't specify any R. So, and with the help and thanks to this Y term that I've put here, one can show that the charges do not depend on the value of R where I have put the boundary. And this is actually physically very interesting and appealing because you would think that the details of the degrees of freedom should not depend on where in the space-time you put your boundary. And this is achieved by this choice of Y term. Okay, going through this procedure, one can find the charge variation over this phase space. So this covariant phase space formalism, unlike the Noether procedure, gives us the variation of charge over the phase space. It doesn't give us the charge itself. So this is what one gets through the standard but maybe tedious computation. And the structure of this charge is very simple. So it's linear in the symmetry generators W, Z, and T. We had three of them. And then it has delta of some function over the phase space. Delta omega, delta of omega blah, blah, and so on. But the point is that, so these two Z and W are of this very simple form. The symmetry generators times delta of some function, but the T generator comes in bit more complicated form. It's not delta of a function over the phase space because it's delta times distributive and so on. It's not delta of something. What this means is that this charge variation is not integrable over the phase space because you cannot find the function over the phase space so that this delta slash of q is delta of that function over the phase space. And this is called non-integrability of the charge. And this is why I've used this slash notation. Delta slash shows that it's not a variation of something over the phase space. Okay, then with this, when we face this situation, one can do some different, take some different strategies to move on. One strategy is basically to say that, okay, we can separate this into a part which is delta of something plus the rest, which is called flux. And this is basically how it looks like. We have separated this into an integrable part and the flux part. And for those of you who are familiar with these technicalities, this is the Varnish-Trossard procedure, which basically allows us to separate these two. And this delta slash q is delta of q plus f by definition. On the other hand, one can also compute the Noether charge, basically not going through this covariant phase space formalism, just the standard Noether charge. It basically, if you apply the standard Noether formula to the Einstein dilatant gravity that I showed, this is what we'll get for the Noether charge. But one needs also to correct this for the y term. And then there is also a W freedom in the definition of the Noether charge. If you remember from your undergrad courses, when we add the total derivative term to the Lagrangian, it affects the Noether charge. And this W is exactly that freedom that we have. And we have chosen this in a particular way such that the Noether charge and the charge that the integrable part that I got from this Varnish-Trossard method are equal. So I think this should be possible to do it in general. I mean, to find this W such that the Varnish-Trossard and the Noether charges become the same. Similar remarks has been made in these papers by Friedel and Robley. Okay. Another thing that one can learn from this charge analysis is the so-called balance equation. That if we just look at the expression for the charge, as I mentioned, the functions that appear here are functions of v, and there is no r dependence. So one can compute, and this charge, for example, the Varnish-Trossard charge and the flux are all functions of v. And one can compute the time derivative, the v derivative of this q, and see how it is related to this f. And a simple and straightforward analysis leads to this equation, that the d by dv of the charge is equal to the flux. This is the so-called balance equation. For those of you who are familiar with the similar analysis for the BMS algebra in the asymptotic 3 or 4-dimensional cases, there we are dealing with a similar balance equation. Actually, this balance equation, which is basically coming from the definition of the bracket, Varnish-Trossard bracket and charge, is nothing but an identity once we consider equations of motion. So there is no particular extra context here. However, writing this equation shows non-conservation of charges and how it is related to the flux. It gives some physical meaning to the Barnish-Trossard method. So we, as I said, there could be some fluxes through the boundary, and the boundary degrees of freedom are basically should readjust themselves when a flux of, for example, gravitons or other stuff passes through the boundary. And this is needed, I mean, this readjustment is needed because remember, we are exciting the space-time and we don't see what's behind. So as if, for example, you have a graviton and comes and it dissolves onto the boundary. That's what the observer that I'm considering is viewing. Okay, so this balance equation is telling me how these boundary charges are readjusting themselves due to the passage of the flux. Okay, and I can skip these remarks. Okay, now, the other interesting and important fact here is that at the start I just chose my, sorry for going back and forth, symmetry generators to be of this form, and it was my choice that this T, Z, and W are field independent. I mean, they do not depend on omega, lambda, and eta, which specify points on my solution space. This was a choice. Okay, so you can say what happens if we consider, for example, T to be a function of lambda, omega, and eta, and similarly for Z and W. Okay. There is no physical objection to do so, and actually this basically only amounts to choosing a different set of functions over the solution space. Instead of omega and eta and lambda, you could have taken any other function and you parameterize your solution space in different ways. But this is like choosing a coordinate system on the solution space. I mean, parameterization or slicing on the solution space. And the physics should not depend on the slicing. Here I'm talking about the slicing on the solution space rather than slicing on the space-time. Okay, one can basically use this freedom for a good advantage. And that's basically if instead of W, T, and Z, I introduce these hatted objects, W hat, Z hat, and T hat in this way. As you can see, these are linear in Z and, I mean, linear combinations of Z and T and W, but the coefficients could be field dependent. Okay. With this so-called change of slicing, the charge variation that I just showed, the same expression here, which was not integrable in the original slicing in terms of W, Z, and T, takes this form, which is integrable. Now the coefficients of W hat is delta omega, Z hat is delta pi, and so on. So this is delta of something over the solution space if we assume that W hat, Z hat, and T hat are field independent. So this is an assumption. So it's a change of, by a change of slicing, I can turn my non-integrable charge into an integrable one. So with these field variations. So this particular choice was made because it made the charge integrable, and I can call this integrable slicing. Okay. In this integrable slicing, sorry, hat is missing here. One can compute the adjusted Lie bracket of the symmetry generators, and one finds a simple abelian algebra because this is what we have. And one can compute the algebra of surface charges, and what we find, this is just the standard equations in this covariant phase space formalism, is that this Z and W form a Heisenberg algebra with h bar being 1 over 16 pi g, and the other generator commutes with the rest. The other generator was just this number here. Okay. Okay, so this is what I mean by the Heisenberg algebra. So I guess I can skip this part. But let me make a remark here that as you can see here, the charges are omega pi and this m, whereas in the previous case I had 3 charges which were functions of v. So here I have only 2 functions in this integrable slicing rather than 3. But the point is my phase space is still parameterized by 3 functions, and lambda, as we showed here explicitly, in the symplectic form appears here. And so while it does not appear in the charges, lambda appears in the symplectic form, and I need to keep it to basically specify points on my solution space. Okay. So far so good. Okay, so let me quickly also take you through a similar analysis for the 3-dimensional case. It's a bit more complicated, but exactly the same idea and the same physics. Okay, so Einstein equations, which in 3-dimensional case, I start with this Einstein lambda theory. The value of cosmological constant lambda could be negative, 0, or positive. I'll just keep it 3. And the field equations are just given by which equals to minus 2 lambda g mu. And I start with the solution ansatz for the metric, which is given by specified by 4 functions v, eta, r, and u, and I take phi coordinate, the third coordinate, to be 2 pi periodic, and all the functions to also be periodic. Okay. So once again, v, r, and u are functions, generic functions of r, and v and phi are the coordinates, but eta is only a function of v and phi. So this is a solution ansatz, which is compatible with the choice that I want to put boundary at a given r, a given but arbitrary r. Then I need to impose Einstein equations and solve for these functions, and in 3 dimensions equations are as in 2 dimensions, they are simple enough to be able to solve them, and this is the explicit solution. So as you can see, the r dependence of these r, u, and v functions are completely fixed, and the rest of the functions that you see here are only functions of v and phi. There are 6 of them, omega, lambda, eta, epsilon, u, and m. There are still 2 Einstein equations which should be still imposed, and these are basically equations on m and upsilon. Basically, these are the 2 remaining Einstein equations. So the most general solutions are these, subject to these 2 equations. Okay. So once we solve these equations, we remain with only 4 functions which are specified by solutions, functions of v and phi. Okay. Again, the same story. Once I constructed the solution space, the matrix with this form, with these functions u and r, given in this form, subject to this, I can ask whether the diffeomorphisms which rotate within this solution and one can show that this diffeomorphism written here generated by four arbitrary functions of t, v and phi, namely t, z, w, and y, rotates us within the same solution space. Again, these four functions are functions of v and phi. Okay. You may be surprised that there are some very sort of non-trivial functions of the solution space here, but these are chosen for a purpose that I'm basically coming to. Okay, so again, a matter of terminology, we have super translations, which are basically T, super translations in B, super translations in R, super scaling, and we have now a super rotation, basically the diffeomorphism along the phi direction, which we didn't have in the case. And with this symmetry generator, see the fields in the solution space, the metric, are transforming this particle. Okay. One can compute the bracket of the symmetry generators, but since we have some non-trivial field dependence in the coefficients of size, I need to do the adjusted bracket. It's basically the bracket adjusted for the field dependence of the symmetry generators, and they satisfy this simple-looking algebra. This is basically the t and y part are generating diffeomorphisms on two-dimensional cylinders at the constant r, and these z and w are basically two functions which are rotating scalars under these diffeomorphisms. Okay. And here this very non-trivial field dependence here has been fixed such that here in the algebra of the symmetry generators, I don't see any field dependence on the right hand. So basically, that if we had some field dependence instead of an algebra, we would have an algebraic. But that particular field dependence was fixed such that we get an algebra. Okay. So let's move on. We have a solution space. We have symmetry generators on this, and we can basically define surface charges. One can use either Noether procedure or the covariant phase space method. I'm taking you through the covariant phase space method. We need to fix the y freedom as before. We fix it with this particular form, which removes the R dependence of the charges. And this leads to this symmetry, the surface charges variation. Again, it's not integrable, I denoted by this emphasize this delta slash. And it's given by an integral over codimension 2 surface. So that, remember, I had a boundary at a given R, and at the constant V, an arbitrary constant b on that we basically define our charges by an integral over phi essentially, with a similar structure of this charge variation as before. So note that the integral is over phi with arbitrary functions symmetry generators of z, y, and t, and r and v are basically arbitrary. So the charges that I get here are functions of R and V in general. But the R dependence actually with this choice of the Y freedom do not appear. So although they could have in principle be R dependent, now they with this Y choice they are R independent. Okay. Again, the same story. We have a non-integrable charge. We can use this Varnish-Trossard method to separate the integrable and non-integrable parts. And going through the standard, but maybe a bit tedious computation, we arrive at this. In this case, actually, we have also a central term, which is of this form, but this central term is field dependent because lambda appears. Okay. And exactly because of this, it's the BT charges form an algebra rather than algebra. But okay, one can in parallel also do the neutral charge computation. Again, we need to fix W and Y freedoms. The W freedom, the Y freedom we already fixed. The W freedom could be fixed of this form to basically lead to the fact that the neutral charge and the varnish trots are identical, namely this equation. As I mentioned, the charges are functions of V, and one can compute their time derivative, and they satisfy this again. You can see that on the equations of motion, this is just an identity with similar physical meaning as we discussed. Okay. Again, as in two-dimensional case, since we don't have any propagating gravitons in this three-dimensional example, one may try to find slicing of the solution space in which the charges are integrable. And the slicing could be given in this way. This hatted slicing is basically introduced in this way. These are linear combinations. The hatted generators are linear combinations of the original generators, T, Z, W, and Y, but with field-dependent coefficients. In this new slicing, the charges become integrable and take this simple form. Okay. So this hatted slicing, these charges are omega, pi, epsilon hat, and n hat, which are generic functions of me and phi. In the hatted basis slicing, one can compute the bracket of symmetry generators, which take a very simple form. I'll discuss the algebra in a bit. One can compute the algebra of charges using the standard formula for the charge algebra of the charges, namely the bracket of the two charges generated by C1 and C2 is the charge as the charge associated with the bracket of C1 and C2 up to a central term. And the central term is actually simple to compute and has this form. Maybe this is a bit abstract. Let me show you the algebra of charges explicitly. It's just reading this equation for components. So the algebra of omega and pi is a Heisenberg algebra at any given phi. Upsilons satisfy a bit algebra. M's satisfy something like a bit algebra. If lambda is equal to 0, these M's are 0. If lambda is negative or positive, we have this non-zero sign here on the right-hand side. And upsilon and M basically commute to M, but there is a central term. For lambda equals 0 case, where this is 0, upsilon hat and M hat form a BMS3 algebra. But this omega and pi form a Heisenberg algebra, so all in all, for lambda equals 0, we have a direct sum of Heisenberg and BMS3. For lambda less than 0, actually one can show that this Heisenberg part is still there, but these parts, epsilon and m, are nothing but two Virasoro algebras at Brown-Henry central charge. This is in appropriate units is the Brown-Henry central charge. Okay, so this is what we get for the algebra of charges in three dimensions. Let me also make an important comment that here my charges are functions of v and phi. Whereas, for example, in standard Brown-Henry types or BMS3 analysis, there is no v dependence. The charges are only function of on the codimension boundary. Again, one can go through the computations of the and find this symplectic form over the solution space and so on and so forth. I just show you the outcome. This is just to show that there is a well-defined symplectic form on the solution space. Okay. So so far so good. Let me just give you some concluding remarks and discuss further the physics of this results that first and most important is that in presence of boundaries in the space-time we have boundary degrees of freedom, and in the case where we have a causal boundary, namely the boundary is a time-like surface and so on, these boundary degrees of freedom can have their own dynamics, which is not specified by the dynamics in the bond. So that's for example, in the ADS-CFT is a prime example. We have the boundary degrees of freedom, which its dynamics is not specified by the bond. So this is, as we have shown, is sort of much more general, and it need not be on the ADS space, it not be at the asymptotic boundary. The only problem is to identify the correct boundary data, boundary degrees of freedom, and try to see what the dynamics should be. And to identify the boundary degrees of freedom, we need, so the standard procedure that we have adopted is that we can basically go through this covariant space formalism and find the surface charges associated with these non-trivial diffeomorphisms, the symmetries and solution space, and use these as labels for the boundary degrees. Okay. Once again, we focused on the causal boundary, and there are boundary degrees of freedom which are residing on this. They do not propagate in the bulk, and they have their own dynamics. These boundary degrees of freedom actually interact with what you have in the bulk, and the interaction should be such that, if you want to have a consistent theory, that they readjust themselves through the passage of the flux over the boundary. Okay, so that's the general picture. The balance equation is basically giving us this readjustment, how they should readjust themselves, but it does not fix the dynamics of the boundary degrees. So that's yet to be fixed. And here I focus on 2- and 3-dimensional examples, but these are just warm-ups. And the more general case is higher dimensional, in particular 4 dimensions. There are some interesting and important technical details that I just mentioned and I skipped through. In particular, I mentioned the Y and W freedom in the covariant basis space formalism that should be somehow fixed upon some physical requirement. And the physical requirement I used to fix the Y freedom, also called Y ambiguity, was that I wanted the charges to be independent of R, where I put the boundary, the causal boundary. And the W freedom was fixed upon the requirement that the no third charge become identical to the varnished charge. And basically, with these choices, actually, we have used up or fixed the freedoms that we had in the computation of the charges, and now we can use these charges in an ambiguity-free fashion to label our solution space. In general, as we discussed, the symmetries which rotate us in the in solution space form algebras rather than algebras, but we discussed that by appropriate slicings we can get algebra structures. And let me finish by the comment that we hope that by understanding boundary dynamics, we can shed light on questions regarding black holes, microspace information puzzle, and hopefully reconstruct the AES-CFT. So this is sort of complementary and the reverse of what we heard in the previous talk by Sejid. So basically, here we want to see how far we can move if we start from the block dynamics and try to reconstruct a boundary from the block. Bounded here from the bulk, or at least is degree free. So this is a sort of reverse procedure as we have. Thank you for your attention.